Cool. Hey, Scala, hola. I'm Marcin, and 6 years have passed since I joined Everjam, the company I'm working in. It is actually an extraordinary adventure for me. Back then, my grasp of English was limited, and concepts like JVM, Scala, and functional programming were foreign to me. Little did I know that while actively contributing to various projects, I'd find time to master these skills, and the Keep Growing Everjam's motto became reality. Okay, allow me to introduce you to Bill, our intrepid Scala programmer. While Bill might not be a seasoned expert, he's certainly well-versed in the fundamentals of functional programming and Scala. Now, picture this. 5 years ago, one fine day, our intrepid Scala programmer receives an intriguing proposal. Niche of the niche, a blockchain project written in Scala. Well, the catch? He has only 2 weeks to finish a task related to some kind of doc validation. What could possibly go wrong in such a, straightforward job? Well, buckle up, because this journey is about to take some unexpected twists and turns. Bill dove headfirst into the project's existing codebase, eager to unravel its mysteries. What he discovered was nothing short of fascinating. It wasn't just average blockchain. It was actually this truly amazing directed acyclic graph thing. I won't speak much about the project itself, but I would like to give you some context. However, since the project is open source, you can find it on my GitHub or talk to me later if you are interested. Okay, so let's break down key components of this blockchain. There is the transaction. At the heart of it, there is transaction. It's the fundamental unit representing the transfer of the cryptocurrency from one address to another. Each transaction is not just signed, also proved for security. Blocks serve as an aggregator of transactions, but here's the twist. They construct a directed acyclic graph. Unlike traditional blockchains, these blocks have multiple parent blocks, and they are artfully interconnected, forming this complex structure. What's intriguing is that each block has height property parameter. However, unlike Bitcoin or Ethereum, this blockchain allows for multiple blocks to share the same height. And last but not least, there is a snapshot. Think of it as a periodic dump of data that occurs at a regular interval every 2 heights or something. It captures the state of the blockchain at specific heights, providing basically the snapshot of system data. Bill couldn't help but be fascinated by this blockchain, by its unique architecture, while transactions, blocks, and snapshots wove together in a truly distinctive manner. And his journey had just begun. The mysteries of the DAG-based blockchain awaited for his expertise. As Bill delved deeper into the codebase, he encountered a scene that exceeded even his wildest expectations. What lay before him was a coding nightmare, a tangled net of suboptimal practices, processes, whatever, you name it. And, Bill searched in vain for any semblance of design patterns. It was as the code was or has been constructed without any architectural rules, making it a challenging puzzle to untangle. The principles of functional programming were nowhere to be found. Instead, the code was, synchronous, introducing a layer of complexity that was far from ideal. The ubiquitous this synchronized statement touched the code in countless places. It seemed like an epidemic, causing bottlenecks at every turn. And to make matters worse, getters and setters engage in a cycle of mutual locking, creating a breeding ground for deadlocks. By the way, you see this client post sync. This is the API client. Brilliant idea for creating a never-ending list of all possible cases for post, for get, for other API clients, client functions. Simply amazing. So Bill couldn't help but let out a sigh. He knew that timing this on Rally code base would be a Herculean task. Yet he was undaunted, for he was armed with determination, a love for functional programming, knack for problem solving that could conquer even the messiest code. The adventure had just begun. Okay, we now set the stage for our presentation journey. Our adventure begins in the synchronized swamp, a place where even the slowest creatures like turtles, whatever, seem synchronized in their movements. From there, we descend to the deadlock abyss, a bottomless pit of promises and callbacks that can leave your head spinning. Our path will wind through the fibrous forest, a mysterious realm inhabited by creatures, feeble creatures that love to tangle up your threads. We'll traverse through the concurrent canyon and parallel peaks where tasks split as Humpty Dumpty, but hopefully get put back together. And our journey won't stop there. We'll continue upwards to reach the async nirvana, a place where time is relative and events have party on their own. So fasten your seatbelts and get ready. Get ready for the ride through fascinating software development challenges. Okay, managing synchronization manually can be error-prone, complex. It requires a deep understanding of thread interactions and careful handling to avoid issues like deadlocks, live logs, starvation, whatever. And it doesn't scale. In modern concurrent systems, where scalability is essential, heavy reliance on this synchronized or something like that, it doesn't easily allow for fine-grained locking, control over locking, and it makes it challenging to scale to large numbers of cores or to distributed environments. So as you see, the synchronized was epidemic. But Bill got the first task to make some validation. Okay, so to conquer his daunting task, Bill made a strategic decision. He turned to the cats library for the validated monads with the power of recusing or some other fancy things. Basically, he managed to validate this trio block. But let's not forget that Bill's, he invested countless hours, night after night, untangling the net of mysteries that shrouded the codebase. And then, like a bolt of lightning on a clear night, Bill stumbled upon a unit test. But this wasn't just any test. It was a test that was producing a JSON output for a visualization tool available on the project's website. That was this moment everything clicked into place. It was nothing else than pure magic. Anyway, Bill not only successfully completed the initial task, but also unlocked the door to new opportunities. The job was his, and with it came a fresh set of exciting challenges. Bill's journey was far from over. It was just the beginning of his adventure in the world of distributed ledger protocols. Well, with Bill's triumph over his initial challenges, the next task was to integrate an external database, whether it was LevelDB, SwayDB, you name it. This task appeared to be quite simple, right? However, there was a catch. The entire code base was plugged by logs and basically ran synchronously. So Bill devised a plan. He opted for a gradual refactoring approach, taking it one step at a time. His destination was the IO from cats effect. everywhere without unsafe run sync or some other statements. Okay, so let's shed some light. What is this AO data type? This very powerful tool in the programming languages, like functional programming. Sorry, not languages, approaches or conventions. It serves as a way to handle side effects, such as database operations or communication through the network, or something like that, the I/O, in a pure and functional manner. By encapsulating these effects actually into the I/O type, Bill aimed to transform the synchronous and locked code base into some kind of asynchronous and composable masterpiece. That was the pivotal step towards modernizing this project. Well, one does not simply. The infamous unsafe run sync. It's a double-edged sword in the world of functional programming. While it can be a lifesaver, it's often a sign that you are straying from the path of async, safe, and composable code. And Bill might have successfully fixed a portion of the code, but relying on unsafe run sync can reintroduce synchronization concerns and block the execution of the I/O until it's complete, basically negating the benefits of asynchronous programming. It's a bit like taming a wild beast with a temporary leash. It might work, but it doesn't truly harness the power of functional concurrency. Nonetheless, kudos to Bill for navigating the waters of complex and finding a way to make progress. Sometimes in the midst of the storm, you have to use tools that are available to keep your ship, keep your project afloat. Okay, let's skip this part for a moment, and let's talk about the concurrency itself. The concurrency is a broader concept, but it refers to the ability of a system to execute multiple tasks, seemingly overlapping in time. These tasks may not necessarily be executing at the exact same time, but are interleaved or scheduled by the system scheduler to give you the appearance of simultaneous execution. And in a concurrent system, the CPU can rapidly switch between executing different tasks. This allows for efficient use of CPU time, especially when some tasks are waiting for some input-output operations or other resources. And the concurrency is often used to improve the responsiveness of the system and the scalability. So it can help handle multiple client requests or manage a responsive user interface while performing background tasks. Parallelism, on the other hand, is a specific form of concurrency where multiple tasks are executed in the same time, simultaneously, using multiple physical or virtual CPU cores. In parallelism, each task has its own dedicated execution unit, and they work together to perform tasks concurrently in a true parallel fashion. This leads to faster execution of tasks, especially if the tasks are intensive for intensive operations, for computing or something like that. Whatsoever, to take the full advantage of the parallelism, tasks should be independent. They should not rely heavily on shared resources, because this can lead to slowdowns. Concurrency is like having two queues to a single coffee machine, and the parallelism is like having two coffee machines and two queues, so in the same time. Okay, and I said about shared resources, and managing shared resources is crucial to avoid conflicts and ensure data integrity. Shared resources refer to any data that can be accessed and modified by multiple threads or processes. Common examples of shared resources include files or database connections, network sockets, or some application state, mutable application state. And Bill started with cat effect 2, as this library provides a composable way to handle shared resources safely. Developers need to employ synchronization mechanisms like locks, semaphores, mutexes, or concurrent data structures to ensure that multiple threads can safely access and modify, of course, the shared resource to avoid bugs or data inconsistencies. And in the cats effect, there is a type resource that provides a safe and composable way to acquire and to release the resource, ensuring basically the proper resource management. You can use resource to manage resources such as database and so on, as I said. Everything that needs acquisition or to release correctly and should be released correctly. As an example, Bill found out the function that reads the CSV file. It does some stuff around it and returns a list of addresses and their balances. But Bill was scratching his head, wondering why he saw an increased file descriptors, open file descriptors in Grafana, and it was increasing. Well, in any event of error, the close method would never be called. And as I said, cats effect 2 and 3 offers the resource type to manage the lifecycle of shared resources. So we can write something like that to make sure that the file we are opening, we are acquiring the file correctly, we are closing it all the time, and we can use this file resource wherever we want. Okay, resources, fine. But what about some simpler things? What about an atomic state, internal state? There is a ref. There is the concurrency primitive that allows for safe and concurrent mutable state within the context of functional programming. And this reference can be read, can be modified atomically, ensuring thread safety and composability in concurrent programs. And this is a similar concept to mutable variables in imperative programming. But it's designed to be used directly as a functional thread safe in a thread safe manner. Okay, and Bill, while he was familiar with basic functional programming, it's important to provide him some guidance regarding thread safety when using ref. Nobody told him that simply performing a get followed by a set operation without considering concurrency issues isn't the best thing to do in a distributed system. This is the graph of the CPU usage that we had in the project at the time. Oops, 100%. So let's help Bill clean up the mess and guide him towards using ref safely and effectively. When working with ref, you need to know that it's crucial to use atomic operations like update or modify, and these operations ensure that the value is updated atomically, preventing race conditions and maintaining the thread safety. However, there is a subtle detail you need to know, that the inner function you pass to the update, to the modify, or methods like that can be executed more than once. What does it mean? The function must be pure, no side effects. And the reason is that atomically, the atomic modify and update is inside implemented as looping and checking whether the value has changed between reading it first and applying the update. If it has changed, basically it triggers the update based on the new value. So it keeps looping and looping and looping until there was no change. And this guarantees that updates are atomic and consistent in a concurrent environment. And this functional style eliminates mutable state concerns and ensures that the concurrency code remains clear, predictable, and safe. So it's essential to support Bill as he continues his journey to explore the concurrent programming and gradually becomes more familiar with thread safety principles. Okay, so let's shift our focus to another intriguing topic, like a fiber. Picture a fiber as a acrobat carrying a specific action, but these fibers are not light, are like light threads. However, let's clarify that fibers are not the threads itself. When you spawn new fibers, it's not a guarantee that the action will be run, because if the thread pool is running low on threads, these fibers will actually wait their turn. And here's where fibers really shine. Unlike threads, they are incredibly cheap. And you can create an army of these little guys, and we are talking millions, without breaking a sweat and without causing problems for system speed and performance. It's like having an army of tiny, efficient helpers that won't bog down your machine. Quite impressive feats, I must say. And Cat's Effect 2 is the old version of Cat's Effect, but it was like a treasure chest of concurrency at the time, offering us some tools to orchestrate our concurrent fibers. There are tools also like deferred, that's semaphore, mutex, ref that we touched on that before, and it's like a Swiss army knife for shared mutable state in the world of concurrent programs. But here's the real kicker. Cat's Effect recycle threads when a fiber hits a roadblock. If a fiber gets stuck, no problem. The thread it was using gets a second lease, and it becomes available for other fibers to jump in and do their thing. And when a fiber wraps up its task or gets cancelled, those threads basically are ready to get a new task to do, new quest. However, there is a gotcha. If a fiber is blocked by an external action, like waiting on input from a TCP socket or any other I/O operation, I/O I mean input-output, we are in a bit of a pickle. There is no magic spell to whisk it back until that external action completes and finishes. Why is all a big deal, you may ask? Well, imagine you are in a scenario that you have only 4 CPU cores, and you would want this cores to be as agile, juggling tasks left and right, and caring about how threads are used and recycled becomes quite a high-wire act in such a tight space. Our intrepid Scala programmer might not be a seasoned expert, as I said at the beginning, but Bill knew that to keep the CPU cores from feeling like they're stuck in a traffic jam, to do that he needed to do some thread pool juggling. And where did he turn for guidance? None other than Daniel Spivak and titling Gist on thread pools. So let's break it down and easy. First, we've got up with the CPU-bound thread pool. This one needs to be pre-allocated and set to match the exact numbers of CPUs at hand. It's exclusively reserved for tasks that hog the CPU, no distractions. To steer clear of any CPU-bound blockage, make it a golden rule to offload all those blocking operations into a separate thread pool. This one is cached, unbounded, and ready to handle whatever comes its way. And there is no need for pre-allocation or limiting it. And then there is the third one, the asynchronous I/O pool. Because this unbounded is kind of synchronous, this is the asynchronous for actually closely monitoring the application and constantly checking with the kernel for any async I/O notifications. If there is, it should be a small elite team of threads, I mean 1 thread, 2 threads only. And these threads get a VIP treatment with maximum priority because they are the ones responsible for keeping the application low on latency. So they are like conductors, ensuring everything runs smoothly. So Bill certainly had his hands full, but he knew that with the right thread pool choreography, he could keep the Scala performance in a perfect harmony. Well, not really. You see, Bill wasn't entirely sure which operations were CPU bounded and which ones were unbounded. We had the serialization, we had some validation, we have some mappings, and so on and so forth. And especially for this mysterious kernel async IO, they were like messages from another dimension. So he did what any brave programmer would do. He tried to do his best to assign those thread pools somehow. And to navigate this landscape, Bill leaned on the contexts of context shifts from Cat's effect. It's a bit tricky best, because context shift gives you a tool like shift and like eval on some execution context. And it performs some kind of logical forks in your code. And to create a context shift, you just need to pass the execution context, that's all. And this way you can have both bounded context shift, unbounded context shift. But here's the twist. When you shift, you better shift back. Sounds simple, but not so much in the real application life. Poor Bill found himself in a year-long game of hide and seek, trying to figure out if his code was actually dancing on the async IO or unbounded thread pool. It was like a mystery novel. But hey, that's the life of Scala programmer. The tale of Bill's epic journey through the labyrinth world of Cat's Effect 2 had its share of twists and turns. But after what felt like eons, he finally managed to bring kind of stability to the application. Success in his eyes meant the application could work for a whole week without hiccups and giving Bill a well-deserved nap. Then, with the wisdom of a battle-hardened programmer, Bill laid down the law. The code base had become too complex, so tangled. If anyone wants to build upon it, there was no choice but to start fresh. And so it happens. Bill persuaded the client and the team. Their plan? Well, it started with a simple things like updating the dependencies. That was the time to breathe new life into their stack. Also, the holy grail of programming, a log-free code base. It was the promise of a dreamland. And with renewed energy and clear vision, Bill and his team set out on the quest for brighter, more maintainable feature. And just as Bill and the team were gearing up to update their dependencies, they stumbled upon a true game changer, Cat's Effect 3. It wasn't just an update, it was a complete rewrite, so also a fresh start. In this brave new world of Cat's Effect 3, some familiar abstractions have been removed, others had changed their roles and responsibilities, and new abstractions had taken center stage. But there was the monumental shift that left Bill scratching his head. The disappearance of the beloved context shift. That's right, the context shift that Bill had spent a year or two wrangling with was no more. No longer he did need to worry about shifting threads back and forth. No longer required manual thread pool gymnastics. But hold on a second, you might think that, well, what about all that hard-earned expertise Bill had developed through managing threads by hand? Well, that's the secret sauce of the Cat's Effect 3. They employed the same thread pool pattern, but now it was like a magic happening inside the Cat's Effect 3 behind the scenes, and thanks to the library internal wizardry. And here is the magic. When you use some kind of eval on, it ensures that application go back to the correct thread pool. It's like a GPS, built-in GPS for your code, guiding it right towards basically safely leading it back home. And what's more, it has the built-in blocking mechanism. So when you hit a blocking operation, it gracefully shifts execution to an internal blocking thread pool, and like a responsible guide, brings it back to the main pool afterward. So Cat's Effect 3 basically takes the thread pool hassle off your place, making your life simpler and code cleaner. It wipes out those gotchas. So it's like having a trusty sidekick that handles all the heavy lifting, and you focus on crafting your masterpiece, your application. So as a result of the refactoring, Bill no longer experienced CPU spikes, and the average CPU usage dropped from 20% before the refactoring to about 2-3% of usage after. So I would say it's a win-win, wouldn't you say? The art of running tasks in the background, like fire and forget, there is a spawn type class that comes to play. In the Cat's Effect 2, you can start a task, and in return, you would receive a fiber. You can either ignore it, so you have fire and forget, or you can bring it back to the main flow when you want to read its value. And Bill, being a seasoned programmer, he was, at the time, carried this wisdom over into Cat's Effect 3. And there was various background jobs in the application actually running, and all started and then left to do their thing without much fuss. However, Bill also faced quite a challenge, an issue. His application was a bit stubborn when it came to shutting down gracefully. It refused to go quietly into the night, I would say. Bill found himself twiddling his thumbs and what felt like an eternity, waiting for the systemctl service timeout to kick in and finally kill the Java process. Well, an exercise in patience, I would say. So Bill, the ever-learning experts, figure out that Cat's Effect 3 and their I/O app had proper shutdown hooks, ready to handle all those graceful cancellations. But there is more. In the world of Cat's Effect 3, there is a new maestro in town, a supervisor. The supervisor is just a resource, following the same familiar acquire and release pattern, but here's the magic. All the fibers that are started under the supervision would gracefully cancel when the supervision would release. It's like having a guardian who ensures that when the show is over, everyone takes the final bow and exit the stage gracefully. So no more waiting for timeouts or battling with processes. And with Bill's newfound knowledge, the application danced, was fine-tuned and perfect. Bravo, Bill. Through the diligent application of various techniques such as refactoring, adopting cats, proper thread management, supervisors, fine-tuning, and so on and so forth, we achieved remarkable efficiency. During an Hypergraph Cover, episode 40, which is a news-sharing event for our project, I have managed to show on live the process of handling a single transaction coming through the validation, the consensus, all the processes that are there in the application, gossiping through network, through multiple layers of the application, all within 8 seconds, and that's impressive time frame for us. And I've also managed to scale it up to process 80K of transactions per second. And what's amusing, it's not a top limit. It's not an ultimate limit. We simply haven't had time for actually more extensive, more expensive tests to uncover the top limit, the upper limit, and boundaries. Okay, so by embracing CATS3, the principles of functional concurrency, Bill reached the async nirvana. He can write asynchronous code that is not only highly efficient, but also easy to reason about, test, and maintain. And CATS Effect 3 provides the tools, the abstractions to unlock the full potential of concurrent programming, usually in a state of blissful, functional, asynchronous development. Thank you very much.